Welcome back to Chemistry Chapters, and today we are looking at one of the most famous and helpful memory tricks in all of chemistry. We are talking about the phrase oil rig. If you have ever struggled to remember the difference between oxidation and reduction, this simple phrase and the powerful image you provided will lock it into your brain forever. The phrase oil rig is a clever mnemonic device used to remember what happens to electrons during a chemical reaction. It simply stands for oxidation is loss and reduction is gain. When we talk about loss and gain in this context, we are specifically talking about those tiny, negatively charged particles called electrons. This phrase helps you keep track of where those electrons are going when two chemicals interact. Let us look at the right side of your image first, which beautifully illustrates oxidation. You see a heavily rusted, deteriorating metal gear. This happens because the metal is undergoing oxidation, which means it is actively losing its electrons to the oxygen in the environment. When a raw metal loses those electrons, its structure breaks down, corrodes, and turns into the crumbly orange rust you see in the graphic. Just remember the first part of our memory trick: oxidation is loss. Now let us turn our attention to the left side of the graphic, representing reduction. Here we see a pristine, shiny, and perfectly smooth metal gear. This represents the concept of reduction, which, according to the second half of our mnemonic, means reduction is gain. When a substance gains electrons, it is being reduced. In real-world industrial processes, we actually use reduction reactions to extract pure, shiny metals from their raw, rocky ores. Gaining those electrons restores the metal to its pure, strong state. To tie it all together, the graphic features a massive offshore oil rig in the background. This is a brilliant visual anchor for your memory. The next time you are sitting in an exam and find yourself confusing the two terms, just picture this giant oil rig sitting out in the ocean. Remember the rusty gear losing its structure, and the shiny gear gaining its electrons back. And you will instantly recall that oxidation is loss, and reduction is gain. By using strong visual associations like this one, complex chemical rules become incredibly easy to master. Our visual journey by exploring how chemical reactions actually get started, and more importantly, how we can speed them up. Every chemical reaction needs a certain amount of energy to get going, which chemists call activation energy. To understand this, we are going to look at the fantastic graphic you provided, which perfectly illustrates the magic of a catalyst using a mountain and a tunnel. Let us break this down into a clear narrative so your text-to-speech software can read it smoothly and naturally. Let us start by looking at the left side of the image, where a young boy is struggling to push a heavy, glowing orange ball up a steep, rocky mountain path. This mountain represents a standard chemical reaction without a catalyst. The glowing ball represents our starting ingredients located at the start line. Before these reactants can transform into their final forms, they must absorb enough energy to reach the very top of that mountain. This massive energy barrier is the high activation energy. As you can see from the boy sweating and straining under the red neon signs, getting over this barrier takes a lot of time and a massive amount of effort. Now, let us turn our attention to the right side of the image, bathed in a bright, glowing green light. Here, the exact same boy is pushing the exact same orange ball, but instead of climbing the mountain, he is casually walking on a smooth track straight through a futuristic tunnel. This tunnel represents a chemical reaction that is using a catalyst. A catalyst is a special substance that speeds up a chemical reaction by providing a completely new, alternative pathway. It essentially bores a tunnel right through the energy barrier, drastically lowering the activation energy required. Notice how both pathways begin at the exact same start line and end at the exact same products line, surrounded by floating chemical molecules. This highlights a crucial rule in chemistry. A catalyst does not change what ingredients you start with, and it does not change the final products you end up making. It also is not permanently changed or consumed during the reaction itself. It simply offers a faster, easier, and much more efficient route to get the job done. The next time you hear the word catalyst, just remember the boy taking the easy green tunnel instead of climbing the exhausting red mountain. Now that we have covered how catalysts provide a faster pathway, Would you like our next script to explore how other everyday factors, like changing the temperature or increasing the surface area, can also speed up chemical reactions? Thermodynamics, enthalpy versus entropy. Welcome back to Chemistry Chapters. I am Gemini, your AI assistant, and today we are tackling two of the most important and sometimes confusing concepts in thermodynamics, enthalpy and entropy. These two forces explain exactly why certain changes happen naturally in our universe. Let us dive into the fantastic graphic you provided and break this down into a clear, continuous narrative so your text-to-speech software can read it perfectly. Enthalpy, the heat content. Let us start with the left side of your image, glowing in a warm orange light. This side represents enthalpy, which is essentially the scientific term for heat. You see a steaming, hot cup of coffee resting on a wooden table. In chemistry, enthalpy is the measure of the total heat content and the energy flow within a system. Scientists represent this using the mathematical symbol dH. Think about what happens to that hot cup of coffee over time. It has a high amount of thermal energy, but as it sits there, it naturally releases that heat into the cooler surrounding air until it reaches room temperature. This constant flow of heat energy from a system to its environment, or from the environment into a system, is exactly what enthalpy measures. It is the universe's way of tracking where the thermal energy is going. Entropy, the measure of chaos. Now, let us turn our attention to the right side of the graphic, bathed in a cool blue light. This side introduces entropy, which is all about chaos and disorder. You see a massive explosion of playing cards scattering wildly and randomly into the air. In science, entropy is the measure of randomness, disorder, or uncertainty within a system, and it is represented by the symbol ds. Imagine you have a brand new deck of cards, perfectly organized by suit and number in a tidy stack. That is a state of very low entropy because it is highly ordered and predictable. But if you throw those cards into the air like in the graphic, they scatter everywhere in total chaos. That is a state of high entropy. A fundamental law of our universe is that everything naturally moves toward a state of higher entropy, meaning things naturally become more disordered and chaotic over time. The perfect balance. When you put these two concepts together, you unlock the secret to why chemical reactions occur. The balance between the heat flowing in or out, which is enthalpy, and the universe's natural desire for chaos, which is entropy, completely determines whether a chemical reaction will happen all on its own. The next time you are trying to remember the difference, just picture the steaming heat of the coffee and the wild chaos of the flying cards, and you will have these thermodynamic principles mastered. We are zooming past the basic electron shells to look at the true quantum mechanics of how atoms bond. We are exploring orbital hybridization. When atoms like carbon want to form stable, symmetrical molecules, their standard electron orbitals just will not cut it. To make the best possible bonds, they have to mathematically blend their atomic orbitals together into entirely new shapes. Let us break down this stunning neon graphic to see exactly how this quantum transformation happens in a smooth, continuous narrative for your text-to-speech software. On the left side of the graphic, we see the unhybridized raw atomic orbitals. The glowing blue sphere in the very center is an s orbital. Surrounding it are three glowing pink dumbbell-shaped p orbitals, cleanly oriented along the x, y, and z axes. Floating above them is the famous Schrödinger equation. This equation reminds us that these shapes are not solid physical objects, but rather three-dimensional mathematical probability clouds where electrons are most likely to live. In the middle of the graphic, we see a massive swirling burst of energy as these atomic orbitals collide and merge. The atom is taking its one s orbital and all three of its p orbitals and mixing them together into a single, unified mathematical wave function. The result of this quantum mixing is shown on the right as four bright green, glowing lobes. These are the brand new sp3 hybrid orbitals. Because they were manufactured from a perfect blend of 1s and 3p orbitals, they are all completely identical in size, shape, and energy. If you look at the blue diagrams on the glass panels to the far right, you will see a familiar shape. Just like we learned in our previous lesson on molecular geometry, these four identical electron clouds carry negative charges and want to repel each other. They push as far apart as physically possible in three-dimensional space, naturally falling into a tetrahedral geometry with precise bond angles of 109.5 degrees. By hybridizing their orbitals, atoms are able to create stronger, more stable, and perfectly angled chemical bonds to build the universe around us.